We'll probably start up the video right now at this point to get into just a rundown for you guys, because obviously I know time's important for everyone here. Just to let you people know that we are recording this in general, so that pretty much purposes that if you guys do want to have record of this afterwards, just to have, if you want to just in general for questions to be answered or for this presentation or anything like that, we will have a recorded copy for anyone who wants it. So I'm going to be disabling my camera just for a quick second and that to share a video initially that we recorded. And then after that, I'll turn my camera back on and we'll get into more just general question and answering. So as mentioned, obviously, we're going to talk about the various types of strip rolling mills and the application they're used for. We'll be talking about a little bit of giving you guys a rundown on how to properly size a mill in terms of assessing your application, which we'll still assist you on at any time. Mostly when I talk about that, I'm referring to mostly in terms of the combination of your bearing size, your roll diameter, production schedules, things like that that are ideal for determining your need for your application. And based on those information, you'll be able to more properly figure out the different types of configurations of mills and which ones might be ideal to your needs, such as the 2-high, 4-high, 3-high, and cluster mills. And then depending on your application, some of you might be running short length material, and we'll talk about the needs about what applications usually serve for that and how we treat those, as well as for continuous coil. And on the continuous coil lines, we'll break a little bit more into the idea of single stand versus multi-stand, depending on production schedules and the process that you need to produce your need. And then finally, we'll get a little bit more into the types of features and some more of a unique mills, such as our laboratory mills for research purposes, as well as our powder rolling mills. Yeah, so it's just a video to give you a rundown of an example of a single stand strip mill that we've done in the past. That this one is running simple continuous coil feeding off between a payoff and take up winders. It's right now we're running simple guide pulleys with lean-on dancer arms in order to act as a speed and tension control loop, as well as running a continuous lubrication to keep the material well lubricated as it's feeding in between the two rollers. So this is just a simple standalone single stand continuous coil reversing mill, just to give you a visual of one of the other types of machines that we provide. So obviously, we just showed you one that was for continuous. Just to give you an idea of more of what we do with on the short length mill side of it, which these are running more for just single straight length pieces. These are a little bit more simple, and usually there's a lot more of a physical handling by the operator in order to accommodate them. But this is to give you just another quick example from a video standpoint of the different types of strip mills that we can provide. So obviously, as I mentioned before, that obviously we can use strip rolling mills for a variety of different applications. Pretty much almost any material that you can name in the metallurgical industry, we pretty much provide machines that accommodate that: steel, copper, lead, platinum, aluminum, so on and so forth, and pretty much for almost any type of industry that you can name for, such as obviously renewable energy, aerospace, military, automotive, medical, precious metal in general, nuclear research, so on and so forth. So depending on what you want to do, we can obviously provide different types of a mill to serve those types of industries and those types of materials. And we can obviously provide them in both for running sheet type of material, both in the hot and cold condition, as well as running powder applications as well for some of the more unique industries. So one of the things that I mentioned that I was going to talk about is obviously just to give you guys a general rundown of how to properly size out a mill. So when we're talking in general on our mills, they can range from extremely small to extremely large. We do mills that can handle up to about 3.3 million pounds of total separating force. Those rolls have diameters as large as about 35 inches, and we've done face widths of about 60 inches and larger in terms of accommodating very wide material, which accommodates with those mills. In terms of running small, we've done rolls as small as 11/16, and we've actually even done some a little bit smaller, but our standard minimums around 11/16. And to give a rundown in terms of on the more smaller end of the spectrum, and to give an idea of usually in terms of what type of what drives and needs for that is there's a few factors. The biggest thing is going to be in terms of your roll diameter, is that your roll diameter has a direct correlation in both your max thickness you can take in a single pass in terms of total reduction, as well as how thin you can gauge. And the reason it works on that premise is that when talking about your roll diameter, the reduction max reduction you take in pass is based on both a combination of your grip and your bearing. But when your roll diameter has a direct effect on the grip.
Any application, you only have a certain max angle that you can have from basically from the point the material first contacts the roll to the point it's in full reduction before the roll will not want to grip it. The larger diameter of the roll, the shallower the angle becomes at a larger thickness, which is what allows a bigger roll to take a larger reduction naturally from a grip standpoint. On the same premise, in order to roll extremely thin, though, you need to exert a certain amount of natural pressure on the system. Pressure is a direct factor of force over area. So a larger diameter roll has a much larger area of contact. It needs thus much more force to create the same equivalent pressure. So to gauge very thin, small rolls work extremely effective at that. So oftentimes in sizing a mill and the configurations, it's really taking a look at your application and in terms of your full range that you want to accommodate in terms of how thin you want to roll and how large of reduction you want to roll, and then assessing the type of roll as well as maybe the roll configurations that can be used to suit your needs. So as mentioned, that there are obviously some different types of configurations. The most common you'll see are the 2 high and 4 high mills, and then in some applications you can run into what are called the 3 high mills and the cluster rolling mills. To give a general rundown on a 2 high and a 4 high mill is, as I mentioned before, a lot of times what we stare at is how thin you can properly gauge, as well as your max reduction capabilities. So when talking on the 2 high mill, we can accommodate, as I said, a variety of sizes from about very small mills that can only do about 10,000 pound bearing capacity up to 3 million. On our 2 high mills, our smallest roll diameters are usually about 3.5 inches, and we've gone up to about 35 inches. And as mentioned, so 2 high mills are probably the most common you see used in the industry because for the most part they're used for primarily taking heavy breakdown in terms of reductions, and as long as you're not trying to gauge too thin, they oftentimes are used also as a finishing mill. 4 high mills come into a factor when we're talking about how thin you want to gauge, as I mentioned. So for applications that you want to roll to very thin, 4 high mills become extremely useful. And the reason why a 4 high comes into play over a 2 high is in a reflection of both how thin you want to roll as well as how much force you exert. 4 high mills, we've done rolls as small as 500 thou, which is about 12.7 millimeters in diameter. So the roll is allowed to gauge extremely thin, but one of the things in return is by going with a roll that small, you are using a very small bearing, you have very little load that the mill can take. So for certain applications, you want to roll thin, but the amount of force material exerts on the system naturally becomes too much for the bearing in a small roll of that size to handle. Other factors is obviously at those high loads, a small roll that might have a wide face width can deflect a lot, which can affect the ability for you to maintain a uniform surface. That's where 4 high rolling comes into place. It's using a much larger backup roll that has a large bearing behind it in order to hold this, in order to basically absorb the force of material under load to protect the system, as well as add a lot of rigidity in order to minimize how much deflection the small roll has as it's exerting that pressure. And so that's basically what happens when you want to transition from 2 high to 4 high, is a desire to roll thin, but the roll that's ideal for rolling that thin, you worry about the ability to handle loads and deflection, so you have a larger roll behind it for rigidity purposes. Obviously, as mentioned, and you see on the slide, we talk about the idea of 6 high rolling as well as cluster mill, which we'll get into a little bit later on cluster mills, which work on that same prospect of basically controlling pressure and maintaining rigidity in order to help the small roll gauge as thin as possible. One other note to talk about when it comes to 2 high and 4 high, there's what we can call combination mills that can run into both the 2 high or 4 high configuration. So when we decide to do that, we end up driving the backup rolls instead of the work rolls. The work rolls are driven through friction contact, which allows us to take the work rolls, the smaller work rolls in and out depending on the application. Combination mills are used for basically one general purpose. For applications where you want to take heavy reductions as well as gauge thin. So you have basically gives you the flexibility of both, where you can run it in the 2 high, where you want to take the large reductions from a grip standpoint, and then switch to the 4 high rolls where you want to gauge thin. Combination mills, in terms of when we provide 4 highs, are probably the most common version of the 4 high mills because they have the most flexibility. The downside is because they're friction contact on the 4 high work rolls, they're a little more limited in how thin you can gauge versus a 4 high rolling mill that's specialized to only run in that purpose by having a direct driven. So for guys in the application in the foil industry or things like that that are only rolling thin and are never doing anything beyond that, a 4-high warp roll driven mill becomes ideal for guys that oftentimes are doing stuff on the R&D side or production side where they might use the mill to take heavy reductions as well as gauge relatively thin but not extremely thin. A combination mill works well to cover them in that versatility. So one of the other applications of type of mills that you see, which is used in the strip industry, it's more common in the rod industry, which for those that also have applications that we'll be going into more detail in a separate webinar, is what we call as a 3-high mill. So whenever in process of rolling, obviously we're talking about a single point of direction. And then depending on what you want to do from a production standpoint, it might be you're only taking a single reduction and running it through, and that's the end of it. For some of you guys who are running short length material pieces specifically, you might be taking a lot of passes or reductions through the mill to get from your starting size to your finish size. With 2-high mills or 4-high mills in a single stand running that way, we basically would be reversing the rolls back and forth, which can be done relatively quickly, but there is a moment where you are stopping and starting the rolls and thus have downtime while it's making that adjustment. What a 3-high mill does is it uses 3 rolls in tandem, and the top and bottom rolls spin in one direction, and then the top and middle roll spin in one direction, and the middle roll, the bottom roll spin in the other direction from a feed line perspective. So with a 3-high mill, you eliminate the need to stop and start from a reversing standpoint. So it's mostly used in applications where there's concerns of heat loss and the style of, and used with basically some levels of automation where we're basically passing it through the upper set of rolls and then passing it back through the lower set of rolls to do the reduction. And as we're going through one set, we're making adjustments on the other. It's it has been used in the strip industry, and thus if there's guys of for you people that have interest in it, we can talk about it in more detail. But as I mentioned before, it's extremely common in industries such as rod rolling and things like that, where you're running specific profiling in the rolls and don't have to worry about making vertical adjustments. So the efficiency of passing it back and forth works at its best at that point because there's no downtime other than literally the moment you're passing it from one end back to the other. You don't have to wait for the machine to make any adjustments in those regards. The final type of rolling is cluster rolling, which is where we get back into the idea of 6-high as well. So 6-high rolling mill is, for perspective, is a rolling mill in which we are using 2 rolls on either side of the warp roll instead of a single direct 4-high roll. What that allows us to do is apply variable pressure in both the front and rear end of the roll as needed based on the material's tendencies and behaviors, which gives it a little bit more gives it a little bit more precision, a little bit tighter to gauge thinner. Cluster rolling then takes it a step further where you can go beyond the 6-high roll and go up to 12, and then from 12 up to 20, and so on and so forth, depending on the applications. The additional rollers and their spreading give you a lot more rigidity to the system with how small of a direct warp roll you have, with how large of a backup roll you have to provide rigidity. They're the best type of mill for running extremely wide, thin applications where the most minute variation in pressure can not just make you not be able to achieve your finish size, but can cause distortions in the material just because of its sensitivity. The downside, though, is by having this much flexibility of adjustment, it's a lot more of a finicky setup. You have to do a lot more work to get it set up to get it right, and obviously it carries a lot more cost and maintenance. So cluster rolling is used for applications that I basically define as where the nature of how thin you want to roll and how delicate your process is has gone beyond the point at which a 4-high mill can suffice. And at that point is when we recommend cluster rolling. If we can cover your needs with a 4-high mill or a 2-high mill, we will always default to that because they're a lot more easy on the operator from a setup standpoint and a maintenance standpoint. But I wanted to include cluster rolling because there are obviously applications that demand it based on how wide and thin some people want to roll in the strip industry. So one of the things I mentioned earlier was the idea of when we're talking just general applications, this is whether you're talking 2-high, whether you're talking 4-high, or whether you're talking cluster mills, is the idea of continuous coiling versus short length. So pretty much anytime you're talking continuous coils, we're mainly talking 2-high, 4-high, or cluster mills. We're not really talking 3-high mills because a 3-high mill is meant to be more of a continuous passing back and forth between a system of a short length piece. Purpose of continuous coiling is obviously from a production standpoint. If you can run larger quantities of product at once, it's much more efficient. You have less downtime while we're making adjustments. You can make a lot more reduction concurrently, and we can run at a lot higher speeds. Usual rule of thumb is when we're doing short length material, the speed of the mill is kept relatively low because it's the amount of time it spends in the rollers Once it becomes significant, once it becomes a fraction of how much time it's going to spend out of the mill makes an adjustment. There's no point from an efficiency standpoint to go any faster. But when you're running continuous coiling, the amount of time you spend the rollers is significantly higher because of the length of the material being much higher. At that point, we can go to much higher speeds. With short length, there are some exceptions, but I'm usually not going beyond usually about 50 feet per minute or 15 meters per minute for most applications. With continuous coil, we can go into hundreds, if not over thousands of feet per minute in terms of speed. The other advantages of when you go with continuous coiling is it allows for you a lot more control on the material. Right off the bat, the biggest issue that plagues people that run short length, which is the material's behavior. Material, when hand fed or fed through an automated conveyor into a mill with nothing on the back end of it, and with no back tension, the most minute variation depending can affect the behavior of how it comes out of the mill. Most commonly, what you'll see is basically the material curling up and matching the geometry of the roll, or camber where it might flow from one side to the other, just based on you having an uneven reduction. And it's just by the nature of, unless your feed is perfect in terms of pressure on both sides, in terms of guiding and everything when you're hand feeding, that can happen. It's unavoidable. It's depending on certain applications and industries, that's not a big deal. Depending on how thick and stiff your material is, that how much that it varies by that affects it could be marginal. For certain applications, though, it can affect it a lot, which is when continuous coiling carries a huge benefit because we can run it under tension. We can have things to regulate the speed to create back tension as the material is coming out of the mill in order to keep it as straight and stiff as possible, which can severely eliminate and reduce the effect of bowing and camber. In addition, the moment we run continuous feed loops, we can integrate other features for things to monitor in line the nature of the material, such as having gauging for monitoring the thickness, as well as if for other types of industries, other type of equipment for monitoring the metallurgical characteristics of the material that can be done in line continuously. When you're running short pieces, having anything that's used from a monitoring standpoint in line doesn't serve as great a benefit, because by the time it notices any type of abnormality in the system, the material is already out of the roll. With continuous, for example, with a gauge system, if you notice that you're starting to run on the high side of your tolerance, we can make the adjustments on the fly to control the thickness right then and there in order to keep it always within your desired tolerance range. So that's the primary reason why, in general, if you can get to a large enough body materials to run in a continuous at once, it carries a lot of benefits from a production standpoint. But I know for many applications and industries, that's not possible, which is why we accommodate both continuous and short length. So when we get one step beyond just talking about generally continuous coiling, we talk about the idea of single stands versus multi-stands. If you're running material of a long enough length that you can have it, you could theoretically have it being in contact with multiple rollers at the same time, multi-stand can start to carry a big benefit. For certain applications and what processes you guys are doing, like I said, there might be a single reduction that you're taking and that's all you need in order to suit your purposes. But for certain applications, especially people that are casting certain thicknesses or getting them in common sizing, the finished size and dimensions you want to be at might be significantly less than the starting, and thus you require multiple reductions. Multi-stand rolling's purposes from a production standpoint is allow you to take multiple reductions at once without having to rethread and reset up the equipment. Obviously, there are limitations depending on the material in terms of how many reductions you can take before it's fully work hard and needs to be annealed, but you can definitely usually take at least 3 or 4 reductions, and with some applications up to 6 or 7 before you need to fully anneal. And that, depending on obviously what you're starting with and you're finishing with, that's huge from a production standpoint. Because one of the biggest things I'll state when it comes to continuous coiling mills is that efficiency at some point is huge. The amount of time you spend, depending on your coil size and things like that you spend taking your coil off, reloading it, and threading the line. Once you get beyond a certain speed, going any faster doesn't serve a great purpose, because you'll be spending more and more downtime changing the coil because of how much time it takes. So the best way in order to get the highest efficiency is to maximize how much you can get out of a single coil run through, so you can minimize how many times you need to physically pass it through the line. And that's where multi-stand rolling carries its best benefits. So We've obviously talked a little about single stand and multi-stand mills and short length and continuous rolling. So these are just gives two examples of some single stand short length mills that we provided in the past of two different sizes used for. One of these was used from a research standpoint at a university. This other one on the right is used in the precious metal industry for gauging extremely thin on a short length sheet. And then this is an example of a multi-stand line where what this customer is doing is they're running a continuous cast of material, which out of respect to them, I will be just leaving it at that and running it through each of the individual mill stands, which are reducing, which the first four are basically acting as simple workhorses. They're taking heavy reductions to get them as thin as they possibly can go. And then the final stand, which is where you see these motorized screw-downs here, is what's used to gauge it very precise for the finished sizing. So this allows them to run at what the thickness that they can appropriately cast at, running through all the appropriate stands to get to their finished size all in one pass for the highest efficiency for production. So that way they can get as much product as they can in a single day out of this equipment. So the final type of rolling we're going to talk about is powder rolling, which is a little different than most of the normal strip mills. But the reason I apply it in the same idea when I talk about strip mills is that the purposes of powder rolling is to take obviously powder of various type of metals or alloys and using compression, converting it into sheet or strip. So once the material comes out of a powder mill, it's in a sheet or strip form. So there are some applications where it's just we provide just standalone powder mills that is producing a sheet and that's the end of it. And there are other applications where the material starts as a powder, we compress it into a strip, and then it runs continuously in strip form into the next piece of equipment in the line to do further reduction and to add more uniformity to the strip. So powder rolling and strip rolling have some natural ties together. The biggest difference is you're going to see, which is right off the bat, you can tell by this, but even the by the reference image here, is that when it comes to powder rolling, you're using a lot of gravity assist. It's single direction. You're never going to run. You can't reverse with powder rolling. So you're running a hopper sifting powder at an appropriate flow rate into rollers using gravity to assist it in there. And then with the rollers, we're providing the necessary compression needed in order to create it into sheet form. Oftentimes with powder rolling, although their gap setting and controls, like with other types of strip mills where you want to really assess your gaps accordingly, get your thickness, you can spend a lot more time looking usually at load cells or other types of devices you provide to monitor the physical force you're exerting. Because when it comes to the compression or to create your uniformity, the amount of pressure you exert on the material to metallurgically bond it from powder into sheet is huge. And that's why, as you see in the image, we use gravity assist to help drive it in while we focus more on the pressure. So this photo here is an example of a powder rolling we provided. So like I said, any type of powder rolling application is gravity assisted, which means the rolls are either completely horizontal, as you saw in the previous image, or the mill tilts at or we tilt the mill physically at an angle, and it's fed it's fed then in at an angle in order to actually have it reduce. This mill here in the image can rotate up to about 30 degrees, and for this customer's application, they're mostly working around a 20 to 30 degree angle in order to sift the powder through to create compression, at which point it would come out the table here and into their next step in the process. So, and then finally, which this is the reason I separate this a little bit more from the rest of the mills, even though on paper, every type of mill I've shown before applies in this industry, is the lab mills. The only reason I separate lab mills from the other ones that obviously lab mills' purposes is from an R&D standpoint. So typically with production mills, we're trying to get as much as we can for one specific product and one specific application. So they're much more specially tuned to running one thing at the highest efficiency. With lab mills, we're taking all the same concepts we've talked about before: 2 high, 4 high, 3 high, continuous coil, short length, etc. And we're trying to design a mill that accommodates a large range of versatility. Obviously, being on the R&D side, it's not production oriented anymore. So it's a lot more about having a lot of flexibility so that it could run in some applications, run both hot and cold, run very big stuff, run very thin stuff. And then with the other elements that usually we include that are in some production mills, but are more commonly you find a lot more of them in lab mills, is what we provide from a standpoint of recording. So in terms of features in general, which we'll talk about a little bit more on the next slides, is there are various types of equipment and features we can provide for machines outside just the mill itself and its reducing. We can provide things for monitoring temperature. We can provide things for controlling temperature. We can provide things for monitoring force. We can provide things for monitoring current, for monitoring strain in the housings, etc. When it comes to lab mills, those features are much more commonly prevalent. You can definitely see them in production mills and various production facilities that use them. But when it comes to the lab side, because I know data is key, the biggest things you see in these mills that usually are providing is a lot more versatility, like I said, in terms of what they're designed to run with. So they're not a specialist on any specific type of material. Instead, they run a variety of things, and that their purpose is to record data while they're doing that for the purposes of the R&D side of it. So obviously, as we've been talking about various types of mill configurations, and I've alluded to different types of screw downs and controls. So now we're going to talk into a little bit more on some of the features of the different types, regardless of whether you're talking 2 high, 4 high, 3 high, continuous coil, anything else, in terms of features that you can find on any type of mill. So the most basic type is the mechanical hand wheel screw down. These are mainly used for applications where adjustments not that critical, where you're trying to keep the costs down or things like that. We have an encoder reading to give you the idea of where your position at any time, and you physically are turning moving the upper roll up and down accordingly to gauge for your thickness. So it's usually a lot less precise, and it's more of a set and forget type of adjustment, and it's used for basically 2 types of industries. One is, like I said, where we're trying to keep the cost down, and the second is for applications where you're running more continuous production through multi-stands, and the first handful of stands in the line, them being exact on the thickness reduction isn't critical. Their purpose is to take as heavy a hit as possible. So like I said, you set the position with the mechanical hand wheel in terms of the max reduction you can take metallurgically, as well as that the mill can take, and move, and then basically forget it, which is then where you get to the next 2 types of screw downs, which these are 2 much more commonly used, which are electromechanical and servo-hydraulic. These are what I would call your precise types of screw downs. They can make very minute adjustments in order to gauge accurately. We have encoder reading to tell you exactly where you're at, and you can tell it to move to very exact positions. In terms of usually, depending on the application and how tight encoder we can do. Some are 1,000 adjustments, some can be a tighter than 1,000th of an inch adjustment, as needed depending on your tolerances and how thin you're gauging. And so these are much more, when you're talking about multi-stand lines, when I talk about usually like the idea of breakdown mill and finishing mills, these are what you see on finishing mills. Or if you're talking about a standalone mill that's doing everything, these are the types of things you'll see on that as well, because they are meant to be your precise workhorse, your precise machines to gauge exactly what you want for your finish sizing in terms of accuracy. When it comes to the electromechanical versus servo hydraulics, the rule of thumb I state when it comes to them is that when designing a motor, any type of electromechanical screw down or a servo hydraulic, your purpose you're looking for is either something that can move fast, something that can move precise in terms of very tight motion and accurate, and something that can physically drive under load, which is more common in the continuous coil industry side of this, where you might need to make an adjustment while the rolls are already compressing material, and thus have to have the physical ability to have enough torque to be able to physically drive under load while the material is resisting it. When it comes to those 3 elements in electromechanical, you can make it do 2 of those 3 of those combinations with ease. It's really hard to have electromechanical that can drive under load as well as move quickly, because that really affects the motor size and the reductions in terms of precision of motion. Servo hydraulics, they can do all 3. You can move fast, you can move under load, and they can hold a position very tight and accurately, so they can make minute adjustments. So really, when it comes to electromechanical versus hydraulic, electromechanical is easier from a setup standpoint. It's easier from a maintenance standpoint. It's lower cost. So usually my rule of thumb is I default to electromechanical unless the application demands that we need to make large motions quickly, drive under load, and hold position. And for those applications where that's so critical, that's when hydraulics come into play. And that's when you see them much more common. So they're mainly used on guys I'm trying to gauge extremely tight on thickness. And then the other industries you see is when I'm dealing with customers that want to do hot rolling, because the biggest issue is that they want to minimize how much downtime is between passes. So when you're taking a very heavy hit under heat, you want to be able to then move very quickly to the next position in order to take your next reduction in the pass. So that's where you most commonly will see hydraulics used. So I've talked in general about some stuff on the mills and talked about some just general elements and applications and purposes of what they can be used for. And I've mentioned that there are some additional features that can be provided on them. I mentioned a few of them earlier when we were talking about continuous rolling. Now I'm just going to talk about some more of the other types of features that can be quickly provided. So in general, any mill we provide is going to have full safety data lock guarding. We're a U.S. supplier, so everything we make by default is OSHA. For dealing with customers that are international, we will do stuff in CE, CSA, etc. Whatever is needed from safety, we'll provide the appropriate guarding to meet that. That's standard package with any of our equipment. And then in general, the other two items listed under standard, the roll change rig and drive shaft board, are tied together. Is any mill provided, regardless of how simple it is or complicated it is, we're always going to have some method of a built-in rig with a drive shaft support system. Because at the end of the day, when it comes to maintenance on rolling mills, the majority of your maintenance, by far the vast majority, is your roll assembly. It's your tooling, it's where your bearings is, it's the parts that wear down, it's the parts that you're going to be changing with any type of frequency, and doing regrind work, service work, and replacement work on. The rest of the mill itself is pretty much built like a tank. It's meant to last for extremely long periods of time. There's certain parts in those mills that'll probably last decades, and there are other parts that will mostly just fail at the rate at which electrical parts typically fail. The only exception being is, such as I said, like your tooling and a few other components. So the majority of the time you're doing maintenance on the mills is taking the rolls out to work on them or taking them out to have access to the internals of the mill. So we deliberately designed any modern system nowadays with a built-in rig and a drive shaft support system, with those purposes being to make it as easy as possible to get the rolls in and out of the housings, and from both in terms of just naturally getting them out, and with the drive shaft support, locking the orientation of the drive shafts in their position so you can easily drive the rolls back in without having to fight the alignment of the drive shafts. So those are just standard features in general that we provide with the mill. The other types of features, which we've listed here on the right side, there are many applications, and some I would say are used with high frequency that I would say that are more often than not used, but they're not. But depending on the application needs, they're not always definitively provided. So anytime we're running continuous coil, like I said, speed and tension control immediately becomes a thing that we provide, where we're trying to balance the speed of every motorized device, every reducing device, taking into account things like material elongation and maintaining a proper controlled tension so that we can get the best quality of material and reduce things like I mentioned, just as bowing and camber. One of the common things you'll see in production outlets, especially with running continuous, is the concern with rolls heating up in time, or with concerns with the material and its properties going into the roll under pressure, which is where coolant and lubrication come into the mix. So very frequently, coolant, either internally, externally, or both, it can be provided in the system. When we talk about internally, I'm talking about internally cooling the roll from the inside out through a center tap. And then externally is using nozzles directly at the source at which the material hits the rolls to act as a coolant source for both the material and the rolls. That's very commonly used when there's concerns with, based on the amount of work being done and the production being run, there's concerns with the rolls heating up and thermally expanding, or there's worry with the material heating up and starting to metallurgically break down. That's where coolant is very frequently used. And then lubrication is frequently used as well when there's needs for, based on the way the material behaves, you need to have either some type of lubricant to prevent it from sticking to the rolls, or you're worried about what the roll is going to do for it under reduction from a metallurgical standpoint, and using lubrication can assist. And we can provide simple types of manual applicators to complete flow rate nozzles in order to control how much flow and lubricant that you're applying as you need, and can even, depending on the type of application, make it fully recirculator. So one of the other features I mentioned, obviously, is that's very common in the continuous rolling size is gauge reading, where you can monitor your thickness on the fly and make automatic adjustments. So many applications nowadays where we're running continuous material and tolerance on the front and back side of the strip is huge. We provide gauging. We tie them into a control loop with the final stay in the line, where each gauge communicates with basically the front and rear adjustment, either the motors or the hydraulic cylinders, on that final stand in order to control the thickness and keep it within tolerance the whole time being run. And that's where it's very commonly used. So to skip around a bit to talk about some of the other things. Almost any type of machine nowadays, as long as it has motorized adjustments and things like that, we'll put in what we call an automatic pass scheduling. So we have the ability for you to save and record different gap settings, different speeds you want to go at, and depending on the application, other and features you have, might be other parameters as well, that you can program into the mill and tell to run. Basically, I want to run, for example, like a 5 reduction schedule. So what you want. So you can tell it to, hey, we're going to go to this gap and then reduce it. And then we're going to go to this gap and so on and so forth and run it back and forth through a single mill in order to control your desired size. Or for continuous rollings, you can have a pre-programmed schedule that you hit that loads in all the parameters at each stand in the line for what you want to run from start to finish. So that's very commonly used nowadays, and it's something that we can provide easily. And I would say it's by far more often than not included in the system. Some of the less common ones, but are still, depending on application, things that are used with some frequency, is things such as a data acquisition system. So everything I just mentioned previously in terms of devices such as gauging for monitoring your gap, your screw down encoders for telling your position, your motors in general for telling your current, anything that we have in a system, we provide usually data points for the customer to see in general while running. Data acquisition system is us taking it one step further and allowing you to take all those data points and record them and store them, which is used for primary two purposes. One is general just collecting of data for assessment experimentation, and the other one is used by customers with their purpose being that they've been running production batches, and when something goes wrong in the batch, they can go back and look through the data and see if there's anything that the machine picked up, either through like the load cells, the motor torque, or any of the settings that was atypical in order to help them more assess root cause of where the problems occurred. So data acquisition system in general is extremely commonly used in mills, and I would say it's, when it comes to laboratory mills, it's pretty much a standard feature that we provide at this point, but it's not provided on everything, which is why it's listed as optional. We finally then get to some of the less common ones, but they're more, I would say, is application specific. So asymmetric rolling, what that premise is when you're dealing with a rolling mill, we usually spin the top and bottom roll at the same speed. And it's just the easiest from a balance and a control standpoint. But for certain applications, and more commonly, I would say extremely more commonly, this is a thing in single stand lines where you don't have tension, there can be concern with the material bowing up or bowing down to the curvature of the roll and trying to minimize that effect. Asymmetric rolling, we drive the top and bottom roll separately, and you can deliberately vary the speed of them. We set limits, obviously, electronically speaking, on how much you can vary them, but the purpose of varying them is to counteract issues. So for example, if you notice that your material is typically bowing up when you're short feeding it through a mill, if asymmetric rolling, you can drive the top roll slightly faster than the bottom roll. And what that does by having the top roll drive slightly faster than the bottom roll, it naturally forces the material down. But asymmetric rolling, like I said, its primary purpose is used for applications like that. And it's more of a unique characteristic. If you're running continuous coiling with tension, things like that, they're better at eliminating bowing, and having your roll spin at different speeds can cause other characteristics in the system to occur that some may not be good, which is why it's, like I said, this is more of a unique application dependent one. And then another example of one that's application dependent is heated rolls. So like I said, we provide mills that both do hot rolling and cold rolling. When we get to the hot rolling side of it, there are two different things we can do. One is we can provide a mill that can handle whatever heat the customer is putting into the material from the furnace, and that it reduces as quickly as possible so we can get as many reductions as in general in a pass before the material loses too much heat. The next step beyond that is us physically heating the rolls. Now there's limitations how much you can heat the rolls, and depending on the size rolls and things, it can add a lot of complexity to it. But there are two ways we can heat the rolls, either internally through a cartridge heater or externally using inductors. The idea of heating the rolls themselves allows us to basically apply a direct heat source to the material, which can keep it from either for material that's coming out of the furnace, allow it to maintain heat longer, which allows us to take more reductions without having to reheat, or for certain alloys that don't require a lot of heat, such as aluminum, by heating the rolls up to about like 300 centigrade, that might be enough of a heat source for you to reduce it without even needing to use a furnace. And that's primarily purposes where heated rolls come into play. And then the only other purpose that I've used heated rolls in is where the concern with thermal expansion is so severe that the internally and externally cooling the rolls to control thermal expansion isn't good enough. And we deliberately preliminarily heat the rolls up to the point at which they thermally expand so that they won't heat up any further, and instead use heated rolls to do that effect. So those are the primary purposes that heated rolls are used for, which I say most often you see them, like obviously on the hot rolling side of it, for mainly as a way of trying to maintain heat in the material. So the final two things are motorized conveyor tables, which also tie with what I refer to as self-threading and feeding systems. So with certain applications, you could either way, if you're running continuous coil or short length, the product you're running with, we would call is you're concerned with the safety of the operator to physically handle it manually. So for short length pieces, we can use motorized tables with pushers, hold on rolls, various components in order to basically self-grab and feed the material back and forth between the mill and do as many reductions possible automatically, thus eliminating the operator from the equation. And then one step beyond using motorized tables is where I said I get to self-threading and feed systems, which is when you are running stuff such as casting material out of a furnace into a continuous multi-stand line, having the ability for the mill to naturally guide it, knock the material down, and thread it through each of the stands without the operator having to physically touch it is also stuff that is provided because in order to help from both an efficiency standpoint, but most importantly with these two, it's a safety standpoint. Depending on the applications and concerns, we can provide automation of very simple to as complex as you want in order to try to eliminate the operator from the equation of being directly in contact with material depending on what your safety concerns lie. And thus those ones, depending on what you guys want to do and things like that, we can talk about in more detail once this video is over and talk about different things we've done in the past or things we can do to assist from an automation standpoint.
So some of the questions obviously we got asked up front was such as one question I know got asked by a few different people was about whether or not we have compliance curves for our machines. To answer that question, we have general calculations and equations that we run that we can also provide that let you know capabilities of what the machine can do based on your material tensile properties and conditions. That's standard of anything. And then for certain applications and processes, we have done what we call basically roll curve calculations, which that's a lot more material specific. So we've done things where we've run certain types of materials and based on the diameter of the roll, determine how much we can take for our largest hits based on grip, as well as based on starting thicknesses, what we're expecting to get for natural spread, which in strip isn't that much. For round material, you'll see it a lot more. So we have done roll curves and things for that nature as well. And then and just in general, we have calculations that we can provide to and in general as a reference point, and then we can talk more detail on depending on different material properties and hot versus cold, typically what we expect to see from a standpoint of roll grip as a minimum. And then depending on the material tendencies in the roll surface, you can usually get a little bit more, a little bit less than that, but that can at least give you a good median range. So one of you asked a question about whether or not optional features can be added once the mill is installed. To answer your question, some of those features, yes, depending on situations. So one of the things that I'll say that is not easy to install afterwards is whether you want to say, hey, our mills currently runs in 2 high, we want to convert to 4 high. Depending on how much natural space or gap you have in your housing columns, that may be achievable or that may be extremely difficult. When it comes to certain things electrically or other types of features, those can be added on or modified a lot more easily. There's a lot of machines, not just in terms of just doing simple add-on work, but have done full more refurbishments. We've done add-on work where we've basically done upgrades accordingly. One of the big simplest ones to talk about just in terms of screwdowns themselves. So for some customers, they have older mills with simple mechanical hand wheel screwdowns, and we've retrofitted them to be motorized or hydraulic, have done full updated control packages, and can do that without doing too large of an overhaul mechanically on the mill. In terms of other things such as heated rolls, and things like that, those also can be integrated relatively easily. We need to obviously do some modification to the roll design themselves, as well as incorporate a few other things onto the roll chocks and add some additional stuff to the electrics. But overall, a lot of different certain features, yeah, definitely can be added on after the fact as you work on it, if you determine things are necessary. Certain ones, such as like asymmetric rolling, or like I mentioned, 2 high versus 4 high, making those type of changes require a lot larger modification or a lot more difficult after the fact. But we do try to plan at least some level of modularity and to design the mill so certain features can be added on later. So I saw that there was a few other questions quickly asked while I was obviously talking about that. So one was a question I was in regards to wire flattening. So when it comes to wire flattening, we can obviously I can talk about that a lot more. There's gonna be another just general presentation where we're talking a lot more on the wire side of it. Strip rolling mills and wire mills have a lot of overlap, but to give some just general rundown on wire flattening and shaping when it comes to burring, with mills themselves, the generation of burrs in a mill is going to be relatively minimal because you have free flow to the sides. The key when it comes to on the wire flat is how much you're trying to get for natural spread from width to thickness. And that's when I mentioned the idea of roll curves, where the geometry of your roll plus your thickness reduction is going to dictate how much you get natural spread to the sides. And then when it comes to just general flow, when you're trying to then clean up those edges, in order to create your corners or your radiuses, what leads to oftentimes generating of burrs is basically the overflowing of the material into the cavities of the profile that you're trying to make when it comes to shaped work. So with rod rolling or things like that, you also can risk it creating burrs. And that's basically comes down to the idea of you're taking too large a hit metallurgically that when your material wants to flow, it has nowhere to go. So thus it pushes back too much on the open cavities in the roll geometry, thus creating those sharp edges or things like that. When it comes to burrs naturally in the round wire to start with, rolling mills don't remove burrs. They are not a deburring unit. They if they're rolling on a material that already has burrs in it, they usually make them worse. Just to give some general idea of what happens when it comes to burrs in general on that process. So, just some other questions I know that got brought up real quickly, or concerns that some of you had sent ahead of time. One of them I know was regards to C-section and a pre-hardened strip. To give some background, when it comes to shape profiles in general, you can make almost any shape you want using roll and shaping work with proper tooling. You would need some other equipment other than mill to do that. But one of the things I'm going to state is that if you're talking about a true C-sharpen with a C-section with a 90-degree bend, depending on how tight that profile is in the shaping structure, you more likely want to do what's called a forming process, where you're using a different type of rolling machine in order to actually create basically bends in the material instead of actually forming it. If you're trying to shape form material, depending on how tight your bend is and your radius is, material won't naturally want to flow to that level of tightness, and thus having just instead having a device that instead forces it to bend in that shape would be the way to go about this. Obviously, as I mentioned, there are very few that had questions regarding that we cover a variety of different industries, and some of you had, I know, questions specific to more gold bar rolling or titanium. If you want, I can talk about you guys more individually, privately on one specific to your applications. But if there are questions you guys have specifically in regards to certain materials and behaviors, I'm open to answering those questions right now. If you asked a question based on wanting to make a 6 by 0.28 millimeter aluminum wire. So one of the rules to talk about in general, if you're talking on the wire side a little bit, I know this is that usual rule of thumb is that you can improve when you're starting with round material and trying to reduce it to a flat using a mill. It's usually you roughly can double your width with each consecutive pass on average. So if you're talking 6 millimeters wide by 0.28 millimeters thick, you're obviously talking roughly about a 24-to-1 width of thickness. So if you're talking about a round wire section, you would need to do that over at roughly about 4 to 5 reductions in order to get that type of spread. Soft material like aluminum, copper spread a lot more naturally, so that would assist a lot more in the needs. But even so, if you're talking, like I said, roughly 24-to-1 width of thickness ratio starting from round, it's going to be probably about probably around 4 stands to do the reduction work. And you'd probably have your first 3 mills take very large hits to maximize spread, and then you'd use other types of roll tooling in order to obviously clean up on your width afterwards. And there are definitely things that I can assist more offline in giving some general calculations and working with people specifically more on their past schedules and things if they have questions, at least on a surface level, of how to assist when it comes to that. When it talks about roll pointing, was a quick question brought up. We can provide roll pointers. But when it comes to pointing, roll pointers are one way to do it, which we can provide. We also provide other types of equipment such as rotary swagers, which we'll be having a little bit more of a talk to on another presentation when it comes to wire drawing, and which will be another webinar we'll be doing, I believe, next week. For people that have questions more specifically on that, we can talk about roll pointers and swagers at that time. I don't, if you, obviously you guys have any other questions, just let me know. Otherwise, like I said, I don't have a problem with, I know some of you want to be more specific on your process, emailing or messaging us, and I can set up emails or phone communications more privately on certain applications. This is obviously more to give you, which is why we start with the video, a rundown of just things in general, to give you some background and knowledge for trying to get a better idea. And then if there's questions you guys still though have, we can assist accordingly. All right, that's, I think, sounds like we're all good to go. Obviously, like I said, if you guys have any questions, feel free to message me or Annalise and we can set up more of a one-on-one conversations. I hope you guys have a good afternoon.